Hello students and welcome back to my channel. In lecture 4, we are going to talk about monotone sequences. Let us start with the definition. So consider a sequence xn. We say that x is monotonic increasing if x1 is less than equal to x2, is less than equal to x3, is less than equal to so on, less than equal to xn, less than equal to xn plus 1. And this chain of inequality continues. We say that the sequence is monotonic decreasing if we have x1 greater than equal to x2, greater than equal to x3, greater than equal to continuing xn greater than equal to xn plus 1 and so on. A sequence x is said to be monotonic if it is either monotonic increasing or monotonic decreasing. Let us see a few examples on monotone sequences. Consider the sequence x equal to 1, 2, 3 and so on. We could rewrite the sequence as x equal to n. Now you can see that for first value of n, which is 1, the first term of your sequence is 1, x2 is 2, x3 is 3. We'll have xn equal to n and xn plus 1 equal to n plus 1, and this would continue. Now we have a clear inequality that x1, which is 1, is less than equal to 2, less than equal to 3, and this inequality continues for every term of the sequence. Thus we can say that the given sequence x is monotone increasing. Consider the sequence y equal to a square, a cube and so on, where your a is greater than 1. It can be checked that a is less than equal to a square, it's less than equal to a cube, and it will be less than equal to a raised to n, less than equal to a raised to n plus 1. And thus we can say that the sequence y is also monotone increasing. Consider the sequence z given by the reciprocal of natural numbers 1 by n. This sequence is going to be monotonic decreasing. Now there is another category of sequence. So let me give an example. Consider the sequence say x equal to 1, 3, 2, 3, 4, 5, 6 and so on. So it can be seen here that the first 3 terms do not show either increasing or a decreasing trend. But if I look up for from the third term onwards, which is 2, 3, 4, 5, 6, it can be noted that it is increasing. So such sequences are known as eventually monotone. So such sequences are not on the whole monotone, but they start showing a trend after certain term onwards. Now fine with this, but let us just see how can we solve problems based on monotonicity. These were quite elementary examples. In the next section, we are going to see how we are going to solve the examples based on monotone sequences. So I'll be doing a couple and I will be leaving the remaining one for you to practice. Okay, let us begin with the solution. So initially we are just going to list a few terms of the sequence. So if I denote the sequence by capital A, then the first term of the sequence is 2 times 1 plus 3 upon 1 plus 2, which is equal to 5 by 3. The second term of the sequence is 2 times 2 plus 3 upon 2 plus 2, which is 7 by 4. The next term of the sequence is 9 by 6, sorry, is 9 by 5. Then we have 11 by 6 and so on. Some initial comparison between the term values of the sequences will give you the conclusion already. So we need a more theoretical approach which we could write for formal solution. So in this case, what we are going to do is we are going to take into comparison a simple observation from elementary mathematics. So let's say x and y are two numbers. Now if I were to show that x is greater than y, so it is equivalent to showing that x minus y is positive. And if we get that x minus y is negative, again this is equivalent to show that x is less than y. Now the definitions which we have listed above could be summarized in a shorter manner as, now you can see that the successive terms are more than the earlier occurring terms. So we can say that xk is lesser than or equal to xk plus 1 for every k which is a natural number. You could replace the suffixes by n, that's absolutely fine. Now talking about monotonic decreasing, so we have x1 greater than or equal to x2. So as we move on the right, for higher values of n, the term values of the sequence become smaller and smaller. That is, xk is greater than or equal to xk plus 1 for every k natural. So we are going to use the comparison. And if you could see this, so if xk is less than or equal to xk plus 1, it could be clearly proven that xk plus 1 minus xk is going to be greater than or equal to 0. And likewise, for xk greater than or equal to xk plus 1, for every k in natural, we are going to have the inequality that xk plus 1 minus xk is going to be lesser than or equal to 0. So we are going to use these arithmetic to decide the monotonicity of the sequence. So let's go ahead. So in the sequence, in the first sequence, we have an as 2n plus 3 upon n plus 2. So we will also find out the successive term, which will be an plus 1. So an plus 1 is going to be 2 times of n plus 1 plus 3 over n plus 1 plus 2. And that is going to be 2n plus 5 upon n plus 3. Now let us consider the difference between an plus 1 and an. So this is 2n plus 5 upon n plus 3 minus 2n plus 3 upon n plus. So we need to do the basic cross multiplication here. We are going to get 2n square plus 5n plus 4n plus 10. The minus sign in between, we are going to have 2n square minus 6n minus 3n minus 9. And this entire thing is to be divided by n plus 3 times n plus 2. So which is going to be n square plus 3n plus 2n plus 6. Now do note that we just want a comparison between x and y. So we are really not interested what is the difference going to be. We just want to see whether the difference is going to be positive or it is going to be negative. So over here you can see that 2n square gets cancelled. Now we are left out with 5n plus 4n, that is 9n. And we have minus 6n minus 3n, which is another 9n. So this also goes away. So you're left out with 1 in the numerator. And here we have n square plus 5n plus 6. It would be better if I don't simplify it. Let us keep it in the factored form. So which was n plus 3 times n plus 2. Now you can see that the numerator is 1, which is a positive number. The denominator is a product of n plus 3 and n plus 2, both of which are positive. So we can see that this term is going to be strictly positive. Thus, for any n we are getting, an plus 1 minus an is strictly greater than 0, and hence we can conclude that the given sequence an is monotone increasing, and hence it is a monotone sequence. It must be noted that the inequality which we have got here, it is a strict inequality. So it will be better to say that the sequence an is strictly monotone. Okay, now let's move on to the next question. So the next question we have is where Bn is equal to 3n squared plus 1 divided by n squared. So we are going to follow the similar approach. Immediately we are going to find out the successive term of Bn, which is given by Bn plus 1, and that would be 3 times of n plus 1 squared plus 1 divided by n plus 1 whole square. So this is going to give us 3n squared plus 6n plus 3 plus 1, which is going to be 4. And let us keep the denominator as it is, since it clearly gives us the sign on the denominator. Now again, we need to take the difference of Vn plus 1 and Vn. So that is going to be 3n squared plus 6n plus 4 divided by n plus 1 squared minus 3n squared plus 1 divided by n squared. Again, taking cross multiplications, we are going to get 3n raised to 4 plus 6n cubed plus 4n squared minus, now we have n plus 1 whole squared times 3n plus 3n square plus 1, and in the denominator we are going to have n square into n plus 1 whole square. So it is very evident that the denominator is strictly positive, but still we do not have any conclusion about the numerator, so we need to simplify the numerator. So we have a whole square expression here, so we'll be expanding it using a plus b whole square identity, and we are going to multiply this by 3n squared plus 1. So let me keep these terms as they are. So n plus 1 whole square is going to be n square plus 2n plus 1 times 3 times 3n square plus 1, and everything divided by n square upon n square into n plus 1 whole square. So this is 3n raised to 4 plus 6n cube plus 4n square. Now here we could multiply, so we are going to get n squared times 3n squared, which is going to be 3n raised to 4. Then we are going to get n square times 1, which is n square. Now since there is a minus out, we are taking care of that. Multiplying 2n with the binomial, we get minus 6n cube minus 2n, and lastly multiplying 1 with the binomial, we get minus 3n squared minus 1, and this divided by n squared times n plus 1 squared. So let us see some calculations which are happening around. So 3n raised to 4 goes away. Now we have a 6n cube over here, and we have another minus 6n cube that goes off. We have 4n square, we have minus n square, which makes it 3n square, and another minus 3n square. So we get rid of the 4n square as well. So we are just left out with minus 2n minus 1 divided by n squared times n plus 1 whole square. We could just factor out the minus sign from the numerator, so we get minus of 1 plus 2n, and here we have n square upon n square into n plus 1 whole square. Now you could see that for given any natural number, 1 plus 2n is positive. The denominator we already had checked that it is going to be positive, so the fraction over here is positive. But then since we have a negative sign prevailing out, this value is always going to be lesser than 0. Thus we are getting that Bn plus 1 minus Bn strictly negative for every natural number. And since it is a strict inequality, we could say that the sequence given by Bn is strictly monotone decreasing. So I would leave the third and fourth problem to be solved by you people. Let me just add another problem here. So we'll call it as E. So we need to check the monotonicity of the sequence given by xn, which is 1, 1 by 1 plus 1 by 2 plus 1 by 2 squared plus 1 by 2 cube and so on. It ends up at 1 by 2 raised to. It is always advisable to write down the initial terms of the sequence. So let us see what x1 will be. If you will see xn, so xn starts at 1, which could actually be also written as 1 upon 2 raised to 0 plus 1 by 2 plus 1 by 2 square, and it ends up at 1 by 2 raised to n. So there are n plus 1 terms in this summation. So for x1, we will have 1 plus 1 term. So that is going to be 1 plus half, which is 3 by 2. x2 will be 1 plus half plus 1 by 2 square. We already know that this is 3 by 2. So it will be 3 by 2 plus 1 by 4, which is 7 by 4. x3 would be 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube. Again, the sum of these three terms is 7 by 4. So we need to add 1 by 8 to it, and that is going to be 15 by 8. And likewise, we could construct the entire sequence. So we get x is equal to 3 by 2, 7 by 4, 15 by 8, and so on. Now, for testing the monotonicity, we are already given xn. So let us find out the next term, which is given by xn plus 1. So xn plus 1 will be 1 plus 1 by 2 plus 1 by 2 square and so on, 1 by 2 raised to n plus an additional 1 by 2 raised to n plus 1. And like above, we are going to take the difference between xn plus 1 and xn. So if you will see that xn plus 1, which is this, has an extra term of 1 by 2 raised to n plus 1 if you will look at xn. So let me just write it down. So we have 1 plus 1 by 2 plus 1 by 2 square up to 1 by 2 raised to n plus 1 by 2 raised to n plus 1. And then we need to subtract xn from it, and xn is 1 plus 1 by 2 plus 1 by 2 square up to 1 by 2 raised to n. Now a clear comparison is there. We can get rid of 1, half, 1 by 2 squared, 1 by 2 raised to n, and thus we are only left out with the number 1 upon 2 raised to n plus 1. So thus we can conclude that xn plus 1 minus xn is strictly positive, and hence the above sequence given by xn is monotone increasing or strictly monotone increasing. So that's all for today. If you have any questions or suggestions, please put up in the comment box. Thank you so much for watching till